Hey guys, this is Carrie, and this is the answer key for homework number 2 from Unit 3 Factoring. Alright, so we've got simplify each of the following until you have x to a single power. So here we have x to the fourth times x to the third. When we're multiplying two things with a common base, we add the exponents. So we get x to the seventh. Here we have x to the fourth to the third. When you have a power of a power, we multiply the exponents, giving us x to the 12th. Write the following expression with a single radical and a single power. So in this unit, we've been talking about exponent rules. So I think it makes sense to convert these radical problems to exponent problems. So if you remember in the last unit, when we saw things with a root and a power, we could always rewrite that as a fractional exponent. So we have x to the fourth power divided by the third root. And the mnemonic that we had for remembering that, right, was that powers were on the top. So when we have a power of 4, it goes on the top of the fraction. And then just like a plant, the root is on the bottom of the fraction. For the second one, we've got x to the power of 2 divided by the root of 5. So now we've turned this problem, which was a radical problem, into just an exponent problem. We have no radicals left. So because we have two exponents, even though they're fractions, all of the exponent rules still apply. So what we can do here is we're multiplying two things with a common base. Just like in problem 1a, we're going to add the exponents. To add these two exponents, we need to get a common denominator, so we can multiply by 5 on numerator and denominator here, and by 3 in numerator and denominator here. That gives us x to the 20 over 15 plus 6 over 15. So we get x to the 26 over 15. Now converting back to radical and power form, we've got the 15th root, since the root is on the bottom, of x to the 26th power, since the power is on top. So that would be our final answer with a single radical and a single power. Verify the following identity for all values of x and y. Whoa, this looks crazy. So when we're talking about verifying the following identity, it's a lot like when we tried to validate our solutions with the square root problems. So we're not allowed to use any inverse operations here. We just need to evaluate each side separately and make sure that they match. So maybe what we can do is, I know that this side is going to take me a lot more room. So let me write all the way to the left. So we've got the left-hand side, x to the fourth plus y to the fourth squared. What squaring really means is this thing times itself. Wow, typo. This thing times itself. On the left-hand side, and I'll try to be consistent here, we'll do, on the left-hand side, and I'll try to be consistent here, we've got, I'll use green for this side, x to the fourth minus y to the fourth squared, which means that thing times itself. And then we've got this thing squared, and like we talked about in class, we can distribute that exponent to each of the groups. So I end up with 2 squared, x squared squared, which is that whole power of a power thing. So power of a power means we multiply. And here we have a power of a power, so we multiply y squared. 2 times 2 gives us 4. All right, so now continuing on, we've got the left-hand side, which we'll distribute. We get x to the 4 plus 4 is 8. Because we're multiplying, we add the exponents. We get x to the fourth, y to the fourth, and we can't combine those because they're two separate variables. Now we've got x to the fourth, y to the fourth again, keeping things alphabetical. Y to the fourth times y to the fourth, well, we're multiplying two things with the same base, so we add the exponents. 4 plus 4 is 8. On the right-hand side, in green, we're going to have very similar. X to the fourth times x to the fourth gives us 4 plus 4 is 8. X to the fourth times negative y to the fourth gives us negative x to the fourth, y to the fourth. Y to the fourth times x to the fourth gives us negative, and then keeping it alphabetical, x to the fourth, y to the fourth. And then negative times negative gives us positive y to the 4 plus 4, because they're the same base, gives us 8. Now we still have this plus, I'm just going to mark it here, plus 2x. Oh, wait, it's not 2, right? I can actually simplify that one step further. 2 squared is 4, x to the 4th, y to the 4th. All right, so now if we simplify, if we combine like terms on the left-hand side in blue and combine like terms on the right-hand side in green, hopefully these two things are equivalent. So let's see. We've got x to the 8th plus, we've got one of these plus another of them. We've got 2x to the 4th, y to the 4th, plus y to the 8th equals. Now over here, we've got x to the 8th. That's looking good. Now we've got a number of these x to the 4th, y to the 4th terms. So we've got, I'll use a triangle for those. So we've got 1 here. So we've got -1 minus another, that would give us -2. Now here we've got +4 of them. So that's adding 4. So that leaves us with 2. -2 plus 4. 2x to the 4th, y to the 4th when we combine all the triangle terms. And then here in a, in a super zigzaggy underline, we've got plus y to the 8th. And actually, we're done. If we look at the left-hand side and the right-hand side, they completely match. So because both sides simplify to the same expression, they are equivalent. And just so you guys are aware, this was a Regents problem that I actually, from Algebra 2, that I modified to make it a little bit more difficult. It's actually one that's been asked 2 separate times. So for some reason, they really love this identity and making you validate it. This is called a Pythagorean identity because it actually comes from the Pythagorean theorem. So if you want to research it further, this is called a Pythagorean identity. Okay, let's continue on to the back. So completely factor each of the following expressions. So far we only know one method for factoring. It's the greatest common factor method. So we're going to be using that. What's the greatest number that goes into 18 and 27? It's 9. So we have 9. What times 9 will give us 18x? 9 times 2 is 18. We need the x here. 9 times 2x is 18x. What times 9 gives us 27, or -27? That would be -3. So we've completely factored this expression. So factoring is kind of the opposite of simplifying. It's taking something that maybe you would normally distribute out and ending up with that instead. It's sort of like the opposite of distributing. All right, looking at GCF, the greatest common factor for these two, when we look at 15 and 12, the number 3 is the greatest number that divides both of those. Now, greatest common factor means that they actually share some b's in common. When you have b to the 9th, you have b to the 4th within that. So they share b to the 4th in common. Now, 3 times 5 is 15. If we factor out 4 b's from b to the 9th, that leaves us with b to the 5th to give us a total of b to the 9th. And then 3 times 4 is 12. And if we factor out b to the 4th from b to the 4th, we're not left with any b's. So this is our final answer. For problem C, even though it's 3 terms, the same trick will work. 28, 18, and 21 are all divisible by 3. Whoa, by 3. X to the 10th, x to the 8th, and x to the 5th share 5 x's in common. That leaves us with 8x to the 5th, because if we factor out 5 x's, we'll be left with 5 here. 3 times 6 is 18. If we factor out 5 x's from here, we'll be left with 3. 3 times 7 is 21. If we factor out 5 x's from here, we'll be left with no x's. So this is our final answer for here. All right, solve the following equation for x in terms of a, b, and c. So this is like that crazy stumper problem that we had in class, right? And the reason why this is so challenging to solve for x is that we have 2 separate x's. And so we're not going to be able to isolate it unless we can find a way to get a single x. Luckily, now we know the GCF factoring method. Because these two terms share x in common, we can factor out that x, and that will leave us with, well, what times x gives us ax? X times a gives us ax. What times x gives us bx? X times b gives us bx. And the benefit of this new equation is that we have a single x here, which means that we can isolate it using regular properties of algebra. So to get rid of multiplication by a plus b, we divide by a plus b on both sides. And because we have a single x, we're left with x equals c over a plus b. All right, problem 6 looks crazy. To solve for x here, whoa. It looks like it's going to be impossible to solve for x with x in the denominator. So why don't we multiply by x on both sides of the equation to pop it out of the denominator? That gives us ax plus b equals cx. Now the structure of this problem is starting to match the structure of the problem before. We've got two separate x's, and so you might think it will be very challenging to isolate a single x, and you're right. But actually what we're going to do is we're going to try to make use of this greatest common factor technique again. However, we can't use GCF unless the x terms are all on the same side. So in order to make this new problem with a star look more similar to the problem with two stars, let's subtract the cx term so that our two x terms are on the same side. Minus cx from both sides. That gives us ax minus cx plus b. None of those can be combined because none of them are like terms. Equals cx minus cx is 0. Now I'd like to use greatest common factor, but the key word here is common. If I want to factor out the x, all of the terms over here need to have that x in common, and the b does not. So we need to move the b to the other side of the equation, so we're left with just x terms. So we subtract b from both sides. That leaves us with ax minus cx equals negative b. And you notice that even though there's some minus signs here, the structure of this problem right here that I just boxed is very analogous to this problem here. 2x terms equals a non-x term. 2x terms equals a non-x term. So we'll use the same trick. We factor out x from this side. That leaves us with x times a is ax, x times negative c is negative cx. This is all equal to negative b. And now we're left with that single x. So all we have to do is use inverse operations. Divide by a minus c on both sides of the equation. And we get x equals negative b over a minus c. Now if you did things in a different order, you might have an alternative correct solution. Another correct solution for this problem would be x equals b over c minus a, or x equals b over negative a plus c. All of these solutions are correct, and they're all equivalent, but depending on the order that you use to simplify things, you may have gotten one of them. This is the one that I got. Hope this was helpful, guys, and I'll see you in class next week.